This is picoCTF 2025, and today we are going to solve PyTime 2 in binary exploitation. Can you try to get the flag? I'm not revealing anything anymore. Additional details will be available after launching your challenge instance. Before we launch the instance, I want to mention that we've solved a similar challenge a while ago called PyTime, and this one had PIE, which is position independent executable, meaning the address of the code would be randomized at runtime. Let's see what this one does. So let's launch the instance. Connect the program with Netcat. The program source code can be downloaded here. Let's grab it, and the binary can be downloaded here. Let's grab the binary too. Okay, so let's see what we have to work with first. Segfault handler, call functions, win, and main. This looks almost identical to the previous program. One difference, we would get the address of call functions directly. So the program would print the address of call functions, and it was just a matter of calculating the offset to win and subtracting it from whatever random address we would get at runtime to be able to run win on demand. In here, we don't get that, but look. So the program will ask for our name. It would read up to 64 characters, and then it would print whatever we typed back to us. We can't do a buffer overflow because this prevents that. However, if you notice in this line here, it is printing the buffer back to us. This is a common attack where if we supply format tokens like %x or %p, those would get interpreted by printf, right? And so, for example, this is my name, and then %s, and then name, something like that, right? And so whenever this function would be called, the address of name would be put on the stack, and then %s would read that value from the stack, right? In our case, %s is not very useful. What we can use is %x, for example, and that would print 4 bytes from the stack. That's 32 bits, or %p, that is 8 bytes, and that's 64 bits from the stack, right? So with that bit of background information, let's head back to the downloads. Let's look at our file. So it's 64-bit PIE executable, right? So because it's 64-bit, we are going to use %p as a format parameter to print the values from the stack. And the way this works is like so. So we made that executable, and now we've run the vulnerable program, and if we supply it, let's say 4 %p's, we would get 4 values from the stack, which may or may not be useful addresses, and then it would ask us for the address to jump to. And obviously we don't know the address, we're just going to give it a random address, and it segfaults as expected. So how do we get useful information, and how do we make it call win? In the upper window here, we call vuln, and then we hit Shift-Control-O to split our view, and in the bottom view here, let's attach a debugger -p 90 646. So now we are attaching a debugger to our process here. And what we want to do is info proc mappings. So what this does is it displays all the memory segments that this binary has, with the PIE in effect, with ASLR, which is address space layout randomization. And keep in mind that second part, address space layout randomization, if it's in effect, it means that the positions of the stack and heap are also random, in addition to the base address for the executable. So let's take a look at the proc mapping. So we have here our binary, right? It's starting at this address, and take a look at these 6 digits. So 5621, let me highlight them so they're more visible, right? 56212C, right? Keep in mind those numbers because it's important. And then after our code, we have the heap, which is at 562161 and then something else. And then we have the system libraries at a different base address. And then all the way to the end, we have the stack, which again is at a different address, right? So now what we want to do is to display values from the stack and hopefully see something in this range, right? And we should see something in this range because look, in the main function, we have this function call functions, which calls this function. And what this effectively does is it pushes the current program counter somewhere here onto the stack. So we know for sure that a bit of address of main is on the stack. Now it's just a matter of finding it. And so I don't know, let's try with about 20p, 20% p's. And we have to continue in the debugger. And so now we can take a look at our addresses here and see which one of those matches this address space we're looking for. So the first one, 562161, it doesn't match this one, it matches the heap, right? And so we're not interested in that one. We keep going because the heap distance from the code is also variable due to the address space layout randomization. So we can't use this first address. This is something else. We keep looking to see. No, that's still on the heap. So look here. This, if I highlight the first 3 bytes here, it is inside our code address space. And as I told you, it's most likely within main. So now what we do with this, let's copy this address that we're given, and keep in mind is the second to last in our format string, right? So let's copy that. Let's say from stack, we have that address, right? And let's also copy the format string so that we have it readily available. So now we have to find the address of the win function, right? And to make it easier for us to compare, let's add the 4 missing zeros there, right? So that's our address for win. And for comparison, let's see what the base address for main is. And if you look, the address of main is 41 hex bytes from the address on the stack. And it makes sense because main starts here, it starts running, and then it pushes whatever value we have here. So it makes sense that it's bigger than the beginning of main. But our win address is before main, right? So to get the offset from between this address and win, we will subtract, because this is bigger, we will subtract whatever value we got from the stack from the address of win that we got from the disassembler. So let's calculate. We said address from the stack minus address of win. Okay, so offset is 0xd7. Okay, now this won't matter much because we already know the address straight away from the debugger, but what we can do is enter here something, it doesn't matter what. Yep, we finished that. And now let's say in the bottom one here, we copy the netcat command. And now we are connected to the remote server. So the first step, we give it the format pointer. There we go. And remember, the address we were interested in was the second to last, so it would be this one over here. And I'm gonna put it like that, so it's more visible. Let's pad it with 1, 2, 3, 4 zeros. And now that address here is the address here, right? And so if we subtract the offset we previously calculated, D7, is going to move us up to the beginning of the win function that we wanted to run. And so what we have to do is we grab this address, we put it here, and we subtract 0xd7. And if we did everything correctly, this should be the address of win. And there we have it. PIE shouldn't leak. Submit the flag, and there we go. If you've enjoyed this, make sure to hit the like button. If you'd like to get notified in the future whenever I post new solves, hit that subscribe button. In any case, I will see you on the next one. Bye bye.